There you go. Shit. All right, there you go. All right. So, hello. We're gonna be going over homework number 9 and the 5 questions. So, for the first one, we were given a scenario where there was two boats. Boat A, here as you can see in the picture, it was leading boat B by around 50 meters, and both boats were traveling at a constant speed at t equals 0. So the initial velocity was equal for both of them, which tells us is going to help us later on in the problem. The boats accelerate at a certain point, and we know that when B passes A at around t equals 8 seconds and it has a velocity of 225 kilometers, the question is asking us to find the acceleration for boat A and the acceleration for boat B. So for the first part, we know that x initial of boat A is 50 meters and the x initial for boat B is 0 meters, since um, we can establish that by knowing that boat A was leading by 50 meters. So then the next step I took was convert the initial velocities given to us from kilometers per hour to meters per second. And you do that by multiplying the velocity given in kilometers times 1,000 meters divided by 1 kilometer, and then divide times 1 hour over 3,600 seconds to get the conversion to into meters and seconds. And then from there, I did the same thing for the initial velocity of A. And then from there, I used one of the three equations where the velocity of A equals an initial velocity plus acceleration times time. Since time is given and the final velocity of A is also given, we're just solving for one unknown. In this case, it's A of acceleration of boat A. We simply plug in my values and then I got the acceleration for boat A. For boat B, it was the same concept, just different approach. Since we were given the final positions of A and B, I started from there. I started to calculate the final position for A and B because we know it's equal to each other since we know that B catches up to A. So I used the equation x initial B plus V initial B times time plus 1/2 acceleration B times time squared is equal to that of boat A. I set the values and then I simply just solved for the unknown. In this case, it was acceleration for B, and I got it to be 3.02 meters per second squared. And this makes my answer makes sense because, well, we know that B started 50 meters behind boat A, and we are told that at some point, time equals 8 seconds, boat B passes boat A. So that means, so by logic, we know that boat B should have a greater acceleration in those 8 seconds than boat A.
And so I'm going to discuss number 2. Uh, yeah, this problem we are asked to solve for uh, velocity at c, and then velocity of the wake, and then velocity of um, velocity of counterweight w respect to elevator, which is e, and velocity at c relative to e. So there are 4 questions. So for the first one, uh, uh, for the first, I mean the first step, we need to uh divide the diagram into something like uh this, which uh where I make something like S1, S2, S3, S4, and then using the concept of the like uh the length of the rod are always the same, which is our constraint. We can calculate the velocity of c. I mean the velocity, how fast S1 and S2 changes, as well as how fast S3 and S4 changes over the time. Uh, yeah, basically after we make the equation, the length equation, we derive it respect to t, yeah, we got the velocity, something like that. And in for the first part, I got v1 equals to 12.8, and the second part is velocity of the wake, which is 6.4 meter per second. And part three, we are taught to find VCE. So we simply use the values that we got in the previous part. So VCE equals to VC minus VE, and then I got 19.2 meter per second. And then part four, we want to find VWE. So it's simply VW minus VE, and we got 12.8 meter per second. Yeah.
I'd like to add a little bit to that one. I honestly think that I didn't, for that question, you don't have to do any, or you don't have to solve any equations in order to do that at all, right? Because you can understand the heuristic of the work energy theorem, right? Which is what this question is actually asking, right? That means that the work that's happening is the same, right? But you have for F, like an example would be like for E and W, right? There's a relationship of 1 to 1. So the mechanical advantage of the pulley system there is 1. Therefore, you know that the velocity exchange is also 1 to 1, which means that E and W move at the same velocity. And there's a ratio for the other pulley of 2 to 1, right? Which means that as VT does half the force, or if you input a force on VT, then it will do double the force on E. But work is the same, right? Which means that it has to do double the displacement. That's how you know that C moves 2 times as much, right? So you can use that work energy theorem because there's 2ft on E from the left-hand side pulley system, right? Because the work has to be the same, then therefore the displacement is double, which means that as E moves, C has to be double. And then you can use your relative equations for everything else. You add them up. But I think that's for a lot of these questions, that's a really nice way to use the work energy theorem. I just understand the relationship at all times.
Yeah. There are
Yes.
other ways to solve this problem. Mm.
All right. So moving on to number 3. All right. So we're given this picture, and let me just get my word for it. So we're told that a motorist starts from rest at point A here in the picture shown, and on a circular entrance ramp when t equals 0, and the motorist increases the speed of the car at a constant rate and enters the highway at point B, and the driver's speed continues to increase at the same rate until it reaches 75 kilometers at point C. So for part A, we had to find the acceleration, the tangential acceleration between point A and B. So given the 150 meters to be like the actual radius, if you can think about it like that, over 90 degrees or pi over 2 radians, um, we simply just, so what I did is I used the 3 equations when we know that acceleration is constant. It's just physics 2A stuff. Um, Knowing that the final velocity, or well, the velocity at point C is 75 kilometers per hour, I turned that into meters per second. And then from there, I just calculated the distance from between A and C, doing pi over 2, since that's the angle formed between point A and point B, times 150 being the radius, 150 meters, and then add the 100 meters, the additional 100 meters between points B and C. And then from there, I use the equation b squared of c is equal to b initial squared plus 2a and times the difference in position. The final position I used as a value of c, the distance at c from a. So from there, I got my tangential acceleration to be equal to 0.6466 meters per second squared. And then part B was asking us to find the velocity of the car at point B. I just just using the same formula I used the tangential acceleration to find for the velocity of B. Just this case the unknown was solving for velocity of B, and I got it to be 63.83 kilometers per hour. And then the last component was asking us to determine the magnitude of total acceleration when time equals 20 seconds. So at first I was stuck on this problem. I couldn't really I thought it was just plug and chug, but there could be three different scenarios at t equals 20 seconds. The car could be between points A and B, between point B and C, and from point C onwards. And we can determine where the car's position is going to be at depending on the velocity, because we're given a final velocity at C, and then we obviously found the velocity between point A and B. So what I did was solve for velocity between A and B, between B and C, and then from there I just observed the values depending on the velocity value. It would be if we had to use the equation for acceleration, taking into account the normal acceleration and the tangential acceleration, and the velocity at point the velocity at point B it's obviously 62.83 kilometers or 17.4 meters per second, which is greater than the overall velocity. So this told me we had to find the acceleration using the tangential acceleration and the normal acceleration, and then take the magnitude of those two. We found the normal acceleration using v squared over rho, which in this case is 12.99 squared over 150 meters. And I get 1.11 meters per second squared for the normal acceleration. And then I just simply plugged into acceleration equals at plus an squared, and then take the square root of that, and then I got 1.28 meters per second squared.
All right. So this problem is kind of like the problem from before, to be honest. Like number three. Except you're thinking about it flipped 90 degrees, right? You're on a boat. So essentially what's going on is you have a boat that has a constant velocity. So that means that the boat is not accelerating. And then you have a paraglider who's attached to that boat via rope. And then you're asked to determine a few things. One of them is the acceleration and its degrees. And then the other one is its absolute velocity. So the first one to solve, which is the easiest to solve, is its acceleration. So because the boat does not have any acceleration, it's moving at constant velocity, there's only one acceleration that can be occurring. Since it's telling us that the paraglider is moving in a circular path at a given angular velocity, then we know that the only velocity occurring is the centripetal acceleration that he is feeling. And so when we do that, we can actually just solve for the centripetal acceleration at a given time, which is this initial moment at 30 degrees. So we have a angular velocity, which we can transform into radians per second from degrees per second. And then we can use the equation that the v tangent, so the v tangent to the circular path, is the radius times that angular velocity in radians. And that will get us our vertical or our tangential velocity, which we can then use and plug into centripetal acceleration formula that Jose was talking about, which is v squared over rho. Rho is given at 200 meters. And then we have our centripetal acceleration. We also know that the centripetal acceleration is parallel, or at least points to the center of the rotation. So we know that at this given instant, that it must be parallel to the radius, which means that it's at 30 degrees. So it's on the line of the radius. To solve for its absolute velocity, what we can do is, well, we solve for velocity tangent prior. So we can use velocity tangent. And we know that it's given because the question is asking for a given position. We know the angle that the velocity tangent is pointing on. If we were to treat this as a Cartesian coordinate, we know its absolute direction. So we know that it's pointing at 60 degrees above the horizontal